Hi everybody, this is Mr. Short. Today you can see we're going to be talking about chemical bonds and bond polarity, and it relates to objectives 2 and 3 from our pre-post learning concept check. Objective 2 has to do with classifying bonds as nonpolar covalent, polar covalent, and ionic. We do that based on differences in electronegativity. Got a periodic table of electronegativity values down here. This next one is probably new to you. It's about explaining differences in electronegativity and how that relates to the location of electrons between bonded atoms and the concept of polarity. So I think that's probably new to us. To start out, just a little reminder. Remember, in order to describe bonds, what we do is we take the difference in electronegativity values and we use a scale that we're going to create down below to classify bonds as either nonpolar covalent, polar covalent, and ionic. We can also use it to describe bonds as either polar or nonpolar. We'll get to that later because I know that's new. Just a reminder, the definition of electronegativity is strength of attraction for bonded valence electrons. Okay, you might remember that we previously learned that when we take the difference, we can plot the difference on a scale, and from 0 to 0.5, we classify that type of bond as a nonpolar covalent bond. Now, I think previously I told you the cutoff point was 0.7, and I was wrong about that. So we're going to change the difference to 0.5. If the difference is between 0.5 and 1.7, we classify that type of bond as a polar covalent bond. And if there's a really big difference, we classify that difference as an ionic bond. Okay, so we're going to go ahead and create this table right up here. So the cutoff points are 0, 0.5, 1.7, and remember, I just generically put big number because sometimes the information that you get in a periodic table of electronegativity values is slightly different. This is sort of all-encompassing right here. Alright, we can now classify these three different bond types on this scale. So nonpolar covalent, polar covalent, and ionic. And let's talk real quick about this. If there's a really big difference, a difference of greater than 1.7, really the only way that that can happen is if you get a metal bonded with a nonmetal. So a metal from the left of the periodic table bonded with a nonmetal on the right-hand side of the periodic table. That's going to give you the biggest differences. Because remember, this corner of the periodic table, and fluorine in particular right here, they have the biggest electronegativity values. Said another way, nonmetals, they really like to grab onto bonded valence electrons. Their electronegativity is really high. Down here in this corner, we get elements with the lowest electronegativity values, so that would include metals having low electronegativity values. So they want to give away their valence electrons in a bonded pair between a metal and a nonmetal. So again, you'll end up with an ionic bond if you've got a metal and a nonmetal. Big difference. Now, for nonpolar covalent and polar covalent, it really just depends on how far the two elements are located away from one another. If they're located relatively far from one another, it's probably going to be a polar covalent bond. But if they're located relatively close together, or if fluorine is one of the elements, it's probably going to be a nonpolar covalent bond. Okay. So we've talked about classifying bond types as nonpolar covalent, polar covalent, and ionic, and I want to give us a better understanding of what it means for a bond to be covalent or ionic. So for a bond to be covalent, this basically means that the bonded valence electrons are shared between the two bonded atoms. So when you think about sharing bonded valence electrons, I want you to associate the word sharing with covalent. That's in contrast to ionic bonds. Ionic means a large partial transfer of bonded valence electrons. And we're going to model this in just a second. Okay, so whereas sharing is covalent, large partial transfer is ionic. Okay, next concept has to do with bond polarity, and again, I know this is probably new for most students. So the concept of polarity, being polar or nonpolar, I think is something that you're fairly familiar with. In a Zoom meeting recently, I described this as, we all know that the Earth has poles. And the North Pole is electromagnetically the opposite of the South Pole, right? The Earth is a big magnet, and the North and the South Pole are polar opposites. Hear that word opposite right there. We also know that magnets have poles on them. We call them the North Pole and the South Pole on a magnet. Okay, here's what polar means. Polar means having opposite ends of the bond. One end of the bond has the electrons, the other end of the bond does not have the electrons. Okay, because you have a presence of electrons at one end and an absence of electrons at the other end, it creates poles. Okay, so poles means having opposite ends, and it's based on an unequal distribution of electrons. Nonpolar means not having opposite ends of the bond, and this happens because the bonded valence electrons are basically located right in between the two bonded atoms. So let's go ahead and take a look at a couple of examples. We'll take a look at two polar examples first. Okay, so a polar example would be like NaCl. What I'm going to do is I'm going to space the sodium and the chlorine apart from one another, and then I'm going to draw their relative location of the two bonded valence electrons. Sodium has an electronegativity of 0.93. Chlorine has an electronegativity of 3.16. So if we apply the definition of the term electronegativity, remember it's strength of attraction for bonded valence electrons, we can see that because chlorine has a much higher electronegativity, it's got a much greater strength of attraction for the two bonded valence electrons, pulling those two electrons over much closer to it. Now if we take a look back at the definition of polarity, we can see how the poles are created. So remember, polar means having opposite ends. One end of the bond has the electrons, the other end does not have the electrons. So we can see that this end right here has the electrons. Sodium, in contrast, does not have the electrons, creating poles. Poles means having opposite ends, and we should be able to spot that right here. Now, because chlorine grabbed onto a valence electron that used to belong to sodium and pulled it over closer to it, we would now say that chlorine, because it's partially grabbed onto that valence electron, it is partially negative. This is a lowercase Greek delta symbol, and it means partially. Chlorine, because it grabbed onto sodium's electron, maybe it's that one right there, it becomes partially negative. And sodium by default then becomes the opposite. It becomes partially positive. Now we can really see the poles. You see that these are opposite ends. One end is partially positive and the other end is the opposite of that. It's partially negative. Okay, we've got poles because of an uneven distribution of bonded valence electrons. Here's another example like that. Let's say we're dealing with a bond between carbon and oxygen. Again, we can space out the carbon and the oxygen. Carbon has an electronegativity of 2.55. Oxygen has an electronegativity of 3.44. Okay, we can see because of the difference in electronegativity values right here, it's about-ish 0.9, telling us that we're dealing with a polar covalent bond. Because oxygen has a higher electronegativity, it's going to grab onto the bonded valence electrons and pull those bonded valence electrons closer to it and further away from the midline. So I'm going to draw them about right here. See how this difference is about 0.9? This difference right here is over 2. Because this difference was so much bigger, I drew the valence electrons over closer to chlorine, like way up close to chlorine. But here they're closer to oxygen, but they're not all the way over at oxygen. Okay? Now again, because these electrons are not found right in the middle between carbon and oxygen, it creates poles. One end of the bond has the electrons, the other end of the bond does not have the electrons. And because the electrons are closer to oxygen, oxygen becomes partially negative, and the carbon becomes partially positive. Now again, we can really see the poles. To be polar means to have opposite ends. Okay, last example. Let's say that we've got two elements that are really close together on the periodic table. Maybe it's like carbon and nitrogen, and it has to be two nonmetals. So we're going to take an example of a carbon-nitrogen bond. So I'm going to space these apart. Here's carbon and here's nitrogen. Carbon's electronegativity is 2.55. Nitrogen's is 3.04. Now when I take the difference between those electronegativity values, remember difference means subtract, I just take 3.04 minus 2.55, and I get this number. The difference is 0.49, so we should see up here, this is still a nonpolar covalent bond. Okay, nonpolar right at the beginning tells us that this is a nonpolar bond. All right. For that reason, the electrons are basically right in the middle. Now I know they go a tiny bit closer to nitrogen, but not so much closer to nitrogen that we would really say that these electrons are off-center. So for that reason, we're not going to draw a partially negative and a partially positive on either end, because this is classified as a nonpolar bond. Okay? All right, let's kind of touch this up a little bit. I'm going to add some detail to this. All right, this type of bond is classified as a nonpolar covalent bond because the difference is 0.49. We figured that out by taking 3.04, subtracting 2.55 to get a difference of 0.49. Okay? If the difference is less than 0.5, it's nonpolar covalent. Also, if the difference is less than 0.5, we're going to classify that as a nonpolar bond. Okay, I'm going to put in parentheses here, when difference is less than 0.5. I want us to touch this up here as well. The only type of bond on this scale that is nonpolar is a nonpolar covalent bond. So I'm going to put right up here in green nonpolar. It's a nonpolar bond when the difference is 0.5 or less. That means that these two types of bonds are both polar. So I'm going to put polar right here, and I'm going to put polar right there. Okay. Now we're going to go back and we're going to do the same type of analysis for these two. All right, if we take a look right here, in the chlorine-sodium example, sodium chloride, we've got 3.16 minus 0.93. So the difference here is going to be 2.23. Okay, so I've got 3.16 minus 0.93. That equals 2.23. Having a difference of 2.23 puts it up in this category. So you can see it's not only an ionic bond, but an ionic bond is a polar bond. Okay, same type of analysis down here for the carbon-oxygen example. We take the difference between 3.44 minus 2.55. The difference comes out to 0.89. 0.89 is in this category, so we would classify this as a polar covalent bond, which is an example of a polar bond. Okay, so I'm going to go down here for this one. Alright, so we've got 3.44 minus 2.55. That equals a polar bond, polar covalent bond, which is a polar bond. Okay? Alright, so let me zoom out so that we can see the notes in their entirety and do just a little tiny bit of review here. Okay, what I've tried to do is I've tried to color code a couple things, and I'm going to continue with that color coding. So take a look. We've got the definition for electronegativity, and also in yellow we've got an electronegativity periodic table of electronegativity values. We've also got in orange covalent and ionic bonds. I'm going to go back up here and I'm going to highlight nonpolar covalent and polar covalent. Those are both different types of sharing covalent bonds. And I'm also going to highlight in orange ionic. Remember, when we think about ionic, we think about a large partial transfer of bonded valence electrons. In blue down here, we've got definitions and descriptions for polar and nonpolar. And so I'm going to go back up here, and with my blue highlighter, I'm going to highlight nonpolar and then the two polar bonds. Okay, so again, to emphasize